Welcome to the Knowledge Graph seminar. Today, we are in the week 7 of the course, and our focus is going to be on how do users interact with the knowledge graph. In the course, we started off by discussing what is a knowledge graph, and we spent a few weeks talking about creating a knowledge graph. And our focus on last week was on inference, how we do inference with the knowledge graph. Today, we will focus on the user as to how the user goes about consuming the content of the knowledge graph. So the plan for today is that we are going to have two parts to today's session. I will start with an overview of user interaction techniques with knowledge graphs, which is going to be somewhat conceptual and introduce some theoretical concepts. I'll take about 30 minutes to do that, and we'll then switch on to part 2 of the presentation, which will be given by Nathan Wiegand. He has been working at Neeva, where they are building a new search engine, and he's going to tell us about how they are creating knowledge panels for their search engine. So I'm hoping that Nathan's presentation would be a nice complement to the conceptual and theoretical concepts I would introduce, because they actually have a product which they're trying to field. All right, so with that, I'm going to go right into the basic concepts of how users interact with the knowledge graph. Now, the main reason why I got motivated to add a session on this topic was that when we hear people present knowledge graphs, we see pictures as you see on the screen. And looking at these pictures, the question that it raises in my mind is that, well, these are pretty pictures. I see that there are lots of nodes and edges. There is a lot going on here. But if I'm a consumer of a knowledge graph, is this the best way for me to consume the content of the knowledge graph? And the answer for that to me is, at least I'm not sure if this is the best way to present a knowledge graph to the user. And that created a bit of frustration in my mind, and I started looking at this a little bit more conceptually and formally to see, okay, well, if I were to put a knowledge graph in front of a user, how should I think about it? How should I design my interface for the user? And that's how today's session, first part of today's session got put together. So I'm going to start by first giving a little overview of how our users interacting with the knowledge graph. Like, why are they coming to a knowledge graph? Why do they need the knowledge graph? And then I'll do a little survey of different visualization techniques. Like, if we have a lot of content in our knowledge graph and we want to present it to the user, what are some of the techniques we could apply to solve that problem? And then towards the end, I'll talk about structured query interfaces and natural language query interfaces, both of which are core problems in AI research. And in today's lecture, I hope to introduce those two techniques. And in our session on Thursday, we have invited guests who are going to go much deeper into both structured query interfaces and the natural language query interfaces. When people promote the use of knowledge graphs, the usual sales pitch is that while they are easy to understand for users, and usually when that argument is made, it's made in relation to the schema. And it's actually quite correct that many knowledge graphs, their schema is very simple. In this case, we are seeing a property graph schema for a supply chain network. So we have products and we have suppliers. There is a has-supply relationship between products and suppliers. And with products, we have properties such as their types and prices. And similarly, we could have additional properties with the suppliers. So at this very simple level, a graphical presentation of a knowledge graph is perfect, because it just makes it very clear and crisp as to how we are storing the information and what are the key entities we are trying to relate. But a supply chain network will have millions of instances. And if you want to display the instance data, then for displaying the instance data, it's not very clear if we have to use the graphical representation. or whether we should use something different. Okay, so now this slide captures different modes in which a user may approach a knowledge graph. And we can categorize that into 4 different ways of interacting. First, we have a push versus pull mode. A push mode is where there is a batch process which processes the knowledge graph, collects some information, and they're presenting it to the user. The user is not directly sitting in front of the knowledge graph, but maybe the IT department or analytics department at a company, they crunch the data and they present the results to the user. In the pull mode, the user is actually sitting in front of a knowledge graph through some suitable user interface, and they have some question in their mind, or there is some problem they are trying to solve. And for both pull and push mode, we could have a situation where the question the user is trying to answer is known ahead of time. They are approaching the knowledge graph with a fixed question in their mind. And in some cases, we can also have a situation where they actually don't know the question. They just are approaching the system and they want to analyze the data and they just want to be surprised. They're looking for things that they may not have thought of. So each of these modes of interaction requires a different user interface. And it's helpful to understand these different ways of interacting with the knowledge graph as we go about designing the interface to the knowledge graph. So at the highest level, the interaction techniques for accessing the knowledge graph, they use combination of methods. It is not just one method, it's usually a combination of techniques. And these combination of techniques could use techniques such as keyword search, structured queries. You could be seeing the results in the form of tables, or you could be seeing the results in form of visualizations. And I'm going to try to put this in a kind of formal framework, which will help us how to think about how we go about choosing any of these methods. So I'll start off by giving you some general principles of visualization, and then I'll also introduce some best practices we can follow as we are designing the user interface. So these general principles I'm going to introduce, they are based on a paper by Stu Card. It's a heavily cited paper on visualization techniques, and I've tried to extract some salient points from that paper to present to you. So what's the point of visualization? Why are we even presenting data to the user? The overall goal is that we want to amplify the user's understanding of data, because we have millions of records, and what are we wanting the user to glean from it? And we want to make users' job much easier in understanding what is in our data or in our knowledge graph in our case. So one technique, one approach we can take is when we are presenting information to the user, we present to them more information than they might be able to remember at one time. Okay. And to illustrate that, I'm showing here a very simple user interface, which is showing how a person can go about searching an apartment in the Washington, D.C. metro area. So you're seeing the Washington, D.C. metro area, and top of that, we are seeing these dots, and these are the apartments which are available for rent. And within those dots, we also see 2 dots, A and B, which correspond to the workplaces of the 2 spouses who are in this apartment search. So through this interface, we can see that we are not just presenting a set of data points to the user. We are presenting multiple data points, and we are situating and contextualizing them in a way that is meaningful to the user. Another thing we can do to amplify users' understanding of data is to take away the burden of having to look for information. So in this case, you see the filters to the right, and through these filters on the right, the user can control the distance in which the apartment should be shown, and the rent, and the number of bedrooms, etc. So using those tools, the burden on having to look for the apartments that the user might be interested in is reduced. The third thing we can do to amplify a user's understanding of data is to place relevant data next to each other. And this is actually a contemporary example. The data is a little bit old, and this was partly driven by my frustration on the way the COVID information, COVID case counts was being reported. Because in the press, we see that COVID case count is going up, but they don't tell us that data in some context. For example, is this COVID case count worse than the case count for how many people are dying by heart attacks versus cancer, by traditional flu? I mean, how are we supposed to interpret that number, right? And so I always had very huge amount of frustration on, how do I actually understand the number that is being thrown at me? And in this screen, and this actually data I printed by going to the CDC website, because I wanted that information, and I went to the CDC website and I tried to figure out if there is a way I can get this data, and I printed this screen, and you can find that data. And this screen is showing here how the COVID case count was comparing to other leading causes of death, like heart attack and cancer. And you can see that the case count was actually pretty high. And in fact, pretty soon it became very high. It rose very quickly. And as soon as you see the data in this context, you have a more visceral appreciation of the number that is being presented to us. And that, I think, is a very important technique for amplifying users' understanding of data. Another thing we can do is to keep track of the user's attention. And this is an example that we see on pretty much any e-commerce website. As we are searching for products that we want to buy, on the top left corner, we see this little navigation panel through which they are keeping track of where we are in the overall space of products we may want to potentially purchase. Another technique which is very helpful for amplifying users' understanding of data is to provide more abstract view through omission and recoding of information. And we are back to our apartment search example. And here we are seeing these dots, which are abstract view of an apartment. If we click on any of these dots, probably we can find pictures, we can find the exact rent we have to pay, we can find the lease terms, cancellation policy. All of that information is available, but we have abstracted that information into dots, and we're just showing dots, right? Starting with a big picture overview of the information, and then we can drill down into the details as and when we are curious about, or anything that we want to explore further. And then this is something I've mentioned earlier also, that here the user has an ability to interact and manipulate this visualization. They can control these filters. They can zoom in and zoom out on the map and look at certain area more closely. In the modern days, this could be connected to a Google map. So if you're looking for an apartment, you could even go to the street view and see what the neighborhood is like, right? Okay, so these are 6 different techniques that we can use when we are designing an interface, which will help us in amplifying users' understanding of the data. Now, and as we are designing a user interface, we have lots of design choices. There are many different ways we can lay out information on the screen. And there are 6 different things, or 5 different design choices I'm going to walk you through. The first and foremost is choosing appropriate spatial substrate. So if the data we are going to present to the user has a geographical element, it's naturally shown as a map. And this is something we saw in the apartment search example. But if somebody is buying products on an e-commerce site, then map view may not be the most appropriate spatial substrate. But in general, I think when we are starting to design the interface, the first thing to think about is, okay, how are we going to spatially lay out the information on the screen? Once we have chosen the appropriate spatial layout, then the next thing is to choose some markers. These markers are visible things that happen on the screen that help a user in distinguishing between different data points. And this could be distinguishing symbols like squares and diamonds versus lines, or we could draw areas, we could draw volumes to draw users' attention to a particular set of data points. Then we can also have connections and enclosures. And the interesting thing here is that connections and enclosures, a popular form of implementing them is through graphs, trees, and other hierarchical organizations. And people tend to overdo this. When people are doing visualizations of knowledge graph, that's the only thing they will show, right? And the main helpful thing in understanding that connections and enclosures are useful, but they are useful in conjunction with these 5 other different properties or 5 other different design choices we may have for showing the information. Okay, after connection and enclosures, we can choose appropriate retinal properties. And this can have things like what color things are going to be shown in, how crisp they are going to be, what is going to be the hue of the colors, etc. And anytime we introduce any variation, we have to make sure that we are trying to make a point. And we are trying to draw users' attention to a particular aspect of the information we are displaying. Finally, if there is a temporal dimension to our data, animation of data as it changes over time can really help understand its evolution over a period of time. Visualizations themselves can be of 4 different types. We can have simple visualization, which is a straightforward static mapping of data into up to 3 dimensions. So why 3? Cognitive studies have shown that we are able to focus our attention effectively on only 3 things. And that's why usually we don't show information in more than 3 dimensions. But we can compose our visualizations. So we could have 2 separate visualizations or 2 or 3 separate visualizations, and we can combine them and layer them on top of each other to create a combined visualization. Our visualizations can be interactive, and we saw examples of this in the map search example where the user can selectively expand and navigate. We can have movable filters, we can have dynamic queries, etc. And then our visualization can also be attentive reactive in the sense that as the user is interacting with our graph or with our user interface, the system is going to anticipate what is the most useful next thing to display. And one way this is implemented is to track continually the degree of interest that a user may have in exploring a particular dimension, and based on that, suggest to them or in an anticipation, show them the information that might be of great interest to them. All right, so those were some of the general principles we can use in designing of these user interfaces. I'm now going to step through a few best practices. So as a best practice, we can follow a 5-step design process in which our first step should be to identify which variables we are going to map to spatial dimensions. And then once we figured out those basic things we want to show spatially, then we have to see if we can add more information by combining the mappings so that we can increase the number of dimensions that are being displayed. Once we've done that, then the next step is to choose colors to further accentuate and highlight pieces of information. and then add controls for user interaction and for attentive reactive capabilities. The general template for designing an interface, visualization interface, is to always start with an overview. Start with an overview and then provide some dynamic queries, provide some zooming capabilities, let the user have more details on demand, and in some cases provide query interfaces, some of which could be structured, some of it could be based on dynamic filters, some of it could be querying through examples. All right, so I know this was all very conceptual and theoretical. Some of this I could have actually illustrated using demos. For example, the intelligent textbook demo I had considered in the previous lecture, but I figured given we have Nathan, some of these things we might be able to see concretely in his presentation. So I have 10 minutes left. So I'm going to give you a quick overview of structured query interfaces and natural language query interfaces, both of which leverage to some degree AI technology, and they should be leveraged in the context of the overall design. They are not the only way to interact with the knowledge graph, but they could be used as one of the techniques which is provided in the overall design. So the basic idea behind structured queries is that the queries are going to conform to a predefined grammar, and the system can use that grammar for auto-completing a user's query, and the system can also use that grammar to suggest questions in response to partial inputs from the user. So just to illustrate how that might be done, we consider here a very simple property graph schema for a knowledge graph, where we have countries, and countries can have states as their parts. Countries have capital, which are cities, and there are mountains which could be located in countries. So given a property graph schema like this, we can have queries like, tell me the city with the largest area, tell me top 5 cities by the area, give me states bordering Oregon and Washington, give me second tallest mountain in France. Just to illustrate the auto-completion and query suggestion, if the user types in country, then from the property graph schema, we can see that the next thing can only be mountain, state, or city. Those are the 3 options based on what the user has already typed in. If the property graph schema was way more complex, obviously there could be many more choices, but the basic point remains the same, that by looking at the structure of our schema, we have a lot of information about what the legal queries are. So the structured queries can be captured using a grammar, and we are seeing here a grammar which captures many of the queries that I showed you on the previous slide. So as an example, if we want to formulate city with the largest area, then in our grammar, we would first pick geographical region, and then which is going to be the city. And then it could be, that query could be completed using an aggregate relator, which is with the largest and the property. Okay, so this query city with the largest grammar conforms to the BNF grammar that we are seeing here. Now, as a second example, let's take this query top 5 cities by area. So the first component of this query is an aggregate modifier, which is top number. Number could be replaced by any number, which in this case is 5. And then geographical region here maps to city, and property maps to area. Now, one subtlety I should point out here is that in our query, we have top 5 cities, and the completion that I've shown here using the grammar would only have top 5 city by area. That is, the plural form is not correct. Obviously, it is possible to enhance the grammar so that the plurals are handled correctly, but that requires further enhancing the grammar or or making use of suitable lexicons. So as I stated earlier, the grammar allows us to check for legal queries. It helps us in auto-completing the queries. It can also help us make suggestions for completing partial queries. If we want the queries to be natural, if we want to cover a huge range of queries, then we have to work on the grammar. And grammar engineering or improving a grammar is actually the name of the game. And that's why a structured query interface is well suited only for limited domains. If you're working in a very small domain with very well-defined schema, then structured query interface is a great choice because of the scope. We won't have to spend too much time engineering the grammar, and it also helps bound the scope of queries that the user may pose. But this kind of interface is not suited if you are wanting to handle huge number of variations in English language. Because if you're wanting to handle huge variations in English language, we would end up spending way too much time engineering the grammar, and the structured query or grammar-based query approach has difficulty in scaling. And that's why we'll look at natural language query interfaces to see what are some modern techniques that people are investigating on supporting queries which may allow a lot of variations in the input English. So the state-of-the-art technology for natural language query interfaces these days is semantic parsing technology. The core of the semantic parsing technology is still a grammar, but there are some differences, and you will see. And the basic difference is that here, instead of setting the goal that our queries have to be captured in a grammar, we are going to start with a minimal grammar, with a very simple grammar, and then after that, we'll stop doing the grammar engineering. But we will couple that grammar with a semantic parser. And using a large number of training examples, we are going to train the semantic parser so that it can learn to handle the various variations in the input queries. So I'll give you a quick overview of the components of such a semantic parsing system. It has essentially 5 different components: an executor, a grammar, a parser, a model, and a learner. The job of the executor is to actually run the query. So in the context of the kind of queries we've been talking about in this course, the executor is going to produce a Sparkle or a Cipher query that we could give to the appropriate query engine who could execute the query and give us the results. The grammar is a set of rules which is of the form alpha implies beta. And here we are seeing some of the example rules in this grammar. A big difference between the kind of rules that we are seeing here versus the rules we saw in the case of the BNF grammar was that here, the forms that appear on the right-hand side, they are actually the forms which can actually be executed, right? So the grammar is going to give us an executable form of the query. In these examples, I've used abstract executable form like argmax. If you were using Cipher or Sparkle language as a target, then the right-hand side would be appropriate fragment of Sparkle or Cipher, which would define what how the input form of the query should be mapped to the executable form. The model component of the system is a grammar which processes the input query and produces multiple interpretation. And the job of the model is to associate a probability distribution over those interpretations. Because given any input query, it could map to many different executable forms. And some of those executable forms are going to be more likely than the others. And model defines this probability distribution between those interpretations to indicate which ones are more likely than the others. The parser maintains a number of interpretations at each step. And as the parsing proceeds, it does the job of picking the most likely interpretation. And finally, the job of the learner is to compute the parameters of the model so that the model can figure out what should be the probability distribution over the different interpretations it is finding. And in some cases, it can also learn small extensions to the grammar. Overall, building natural language query interfaces, it's extremely difficult problem. It requires amassing a large amount of training data, which is the biggest bottleneck. For most systems, you can get accuracy in the range of 50 to 60% with small amount of effort, but going beyond that is lots and lots of engineering. And there is the question of whether that is a better architecture versus structured query interface is a better architecture. Because in both cases, you have to do lots of engineering to get good performance. In one case, we are doing the engineering to train our machine learning model. In the other case, we are doing a lot of engineering to improve our grammar. And hopefully, we can get more insight into these trade-offs in our session on Thursday, because we will have two speakers speaking to each of these side of building the query interfaces. So to summarize, I want to emphasize that when we are designing these user interfaces, we have to understand how the user is actually going to consume the knowledge graph, whether it's going to be pull versus push, or do they already know what they want to know, or whether it is going to be some kind of a pre-computed analytics which should be produced for them so that they can glean what is most interesting to them. If I could leave you with one thing from my 30 minutes presentation, it is that we should not assume that graphical visualization is the best user interface for a knowledge graph just because we have a knowledge graph, right? Graphical visualization can be useful, can be effective, but it's one of the many different things we could do for presenting the information. And we should not automatically assume that if it's a knowledge graph, it has to look like nodes and edges. In some cases, it may not even make sense to show a knowledge graph. Knowledge graph may be just hidden somewhere in the background. And in general, the ideal user interfaces will use a combination of methods. Could be keyword search, they could be using filters, they could be using structured queries. And those are all the elements we can use in putting together the most effective user interface. But while we are doing that, we should keep in mind the visualization design principles, and especially the fact that the goal is to amplify users' understanding of data, and goal is to help them find insights and answer the questions they have in their mind. And that's what should drive the design of the interface that we put together for them. So with that, I will conclude my part of the presentation. I invite Nathan to present to us how they are going about building knowledge panels for the search engine they're building.
So let me just get this queued up. Here we go. Well, thank you everyone for having me. It's a real honor to be here. Today, I'm going to talk about some work that I did at NEVA, and I'll give you a background of what NEVA is, with Sizu Chang, Max Allen, and Brendan Chong, amongst others. And the context of what we're talking about here today is building knowledge panels for our search engine. We're going to scope it just to knowledge panels. We're not going to do question answering or anything like that. So today is just knowledge panels. So just a brief background on what NEVA is and who we are and why we're doing what we're doing. Here's an example of our search results for the query best headphones. Here you see that there are no ads. The results are prioritized for the user, and they give the user information that is actually relevant to their task. In this case, the reviews from various trusted review sources, along with the prices which they could buy it. The whole idea of NEVA is that we're building a new search engine from the ground up that is not now nor ever will be ad supported. Because of this, we can work just for our customer, the end user. So our incentives are aligned with the user as opposed to with advertisers. Because we're doing this from the ground up, we have to build a lot of features that we kind of maybe didn't even anticipate we would have to build. So as we were onboarding users, we discovered that users come to rely on all types of stuff. We thought initially we could focus on 10 blue links, but then they started asking for weather and stocks. But the number one thing that people wanted was a knowledge panel. So knowledge panels are the thing on the right-hand side of the search results. So if the user issues the query Albert Einstein, they may get a knowledge panel like this from any of the other search engines. So on the left, you have Google, in the middle, you have Bing, and on the right, you have Neeva. And today, I'm going to be talking about how we built the thing on the right. The interesting thing here is that the knowledge panel includes a summary of information from a knowledge graph. In the leftmost case, it's Google's internal knowledge graph, and it has a prioritization of the facts that they show. Google prioritizes the children and the spouse, whereas Bing prioritizes Albert Einstein's height and his siblings. So different search engines have different prioritization, and that's going to come up in ours as well. So whenever you start, you've got to start somewhere. We need the data. And we didn't have a lot of time because users are begging for this. We got to get it out to them as fast as we possibly can. So we started at the obvious place. Let's start with Wikipedia. Wikipedia already has info boxes. Let's just jump right in. And that's exactly how we tried to begin. So an info box on Wikipedia is the panel on the right-hand side that includes the summary of the entity. You see here that Albert Einstein has a born date, a died date, citizenships, etc. The internal representation in Wikipedia is Wikimedia markup, and it contains a descriptor for these info boxes. The challenge is that I've not been able to find a good parser, and B, there actually is a pretty complex type hierarchy on top of this data. You'll note here that it says that Albert Einstein is a scientist, but a scientist is a subclass of human. By this, all of these fields are transformed by virtue of templates that operate on these different types. Even though we had this, and we could just parse the HTML from Wikipedia, or we could process just the Wikimedia, we wanted to build a presentation layer anyway. Going back to our example earlier, we didn't want to see citizenship, as Wikipedia had, above other fields. We were more interested in notable works, for example. So if we have to build a presentation layer anyway, that means we have to have understanding of this data anyway. Also, if we just processed the HTML file, then we would not be able to understand the rich type information. For example, we would not know that this date is in fact a date object. Knowing that it's a date allows us to render the date to the user in their preferred locale format. Wikimedia has decided that they're going to render dates as day, month, year. Some users prefer month, day, year. So we can have that be a per user setting. So given that we need to understand dates and we need to build our own presentation layer, it made sense to jump straight to a knowledge graph. And that's exactly what we did. We investigated DBpedia, but upon investigation, DBpedia is only a little bit bigger than Wikidata, and Wikidata is properly sponsored by the Wikimedia Foundation. Data is now flowing back from DBpedia to Wikidata, so it made sense to us to go to Wikidata, which is Wikimedia's own knowledge graph that they're sharing with the world. And so that's where we're going to focus. Wikidata is your standard knowledge graph. It's subject, object, predicate. They have this amazing browser. Here's an example of it on the right-hand side. You can see various predicates here, sex or gender, and you can see the object associated with it. The object can actually be a list of objects with modifiers. In this case, country of citizenship Albert Einstein was a citizen of the German Empire, Switzerland, the United States, amongst others. And they have modifiers, which is the time in which that fact or assertion was true. In this case, he was a citizen of the German Empire until 1879. On the left-hand side, you can see what the actual data looks like. So Wikidata publishes their data set in 3 formats. There's 2 graph database formats, and then there's 1 flat file format. I'll get to that in a moment. So given this, we've decided to go with both Wikipedia and Wikidata. Specifically, we're going to use Wikipedia to get the summary, the short text at the top, and the thumbnail. And we're going to use Wikidata to get the facts that we render at the bottom. Whenever you're building a project, especially one with rigid time constraints like we had, it's best to start with some set of prioritization of requirements. In our case, the number 1 prioritization was low latency at serve time. There have been many investigations that show that the longer it takes a search results page to render, the more likely a user is to leave. And our job is to serve our customers, so we want to make sure that we render our pages as quickly as possible. So in order to do that, the first thought was, well, let's just load all of these triples that we get from Wikidata into a graph database. Then our task just becomes, can we write a Sparkle query for each fact that we want to render? The problem with that is that now some Sparkle queries are pretty trivial. They're a single hop or one edge from the entity or the subject to the object, but some aren't, and we'll get to that in a moment. And when that's the case, it's now hard to decide how to guess how long a query or an entity is going to take to fetch all of the data we need and transform it into the format we need. Given this, and the fact that our data is reasonably static, we decided to pre-process as much of the work as we could. So what we did instead is we flattened the entity into an intermediate representation in build time. And then at serve time, we use Scylla, which is a key value store, to fetch the entity we want using the Wikipedia URL as the key. And then we transform that intermediate representation into whatever our display format is. So specifically, we trust our search engine. If we see Albert Einstein Wikipedia result in the top 1 or 2 results, then we'll go to Scylla, we'll say, give me the intermediate representation for Albert Einstein, and then we'll transform the dates according to the user's locale into a lightweight representation. And then that is what gets rendered into HTML or into React Native in the case of an iOS app. So first priority has to be fast. We achieve that by doing most of the work in build and as little work as we can at serve time. The second priority is being able to have customizable templates. As I showed before, we want to be able to say which attributes or facts we care about and what order we care about them in on a per type basis. An example where this is really important is while Bing has decided that Albert Einstein's height of 5'9" is interesting, that particular attribute is not super interesting for most humans unless they're athletes, boxers, football players. Things like weight and height are like very important to a lot of consumers of that data. So not only do we need to be able to extract those features from those particular types of entities, but we need to be able to translate those into a locale dependent understanding. Maybe some user in Europe prefers kilograms and some user in the United States prefers pounds. So now I'm going to describe how we did this. So going back to our Wikidata example, Wikidata publishes their data as the knowledge graph itself, but they also flatten the graph into JSON blobs. A JSON blob is all out edges from a single entity. So what I mean is, given an entity, in this case Q937, which corresponds to Albert Einstein, all of the out edges, in this case, all of the predicates associated with it, are flattened into that entity. So it's one hop in the graph. This is stored in a giant JSON file, JSON lines, so you can process this one at a time. And then you can do trivial transformations. So you can say that I care about country of citizenship, but only the most recent one. These are things that we can state. So given this, now we've decided we have to decide how are we going to specify the rules that we're going to use to do the rendering. So let me do things a little bit of last minute change in the order. So what we want to be able to do is we want to say that we have some particular entity and we want to, or some particular type of entity, and we want to be able to specify how that entity would be rendered. So we have this really scrappy tool that we built. And the way it works is an engineer just writes the name of the rule. They define a predicate on which that rule should apply. So in this case, it's an instance of the entity Q341. Sorry, I'm diverting from Albert Einstein for just a moment. In this case, we're talking about free software. Then the user can click Get Examples. Get Examples translates this predicate into a Sparkle query, issues it to the Wikidata public Sparkle endpoint, and gets back the examples that you see below. The user then can click through these, or the engineer can click through these examples and see both the Wikidata browser on the left, so that you can actually see which fields are available and what those values are, along with how we would render it in our intermediate representation on the right-hand side. The fields that we extract are, in this case, founded, which has a predicate, P571, and it is a singleton value. The reason we do this is, in some cases, like born, died, founded, these are singular events in time. There are other times where maybe there's more than one value, like maybe it's teams an athlete played for, but you really only want the most recent one. So we can specify that right here in the tool by just saying we want to extract a singleton value. Secondly, we can specify a rule that is a list. So we want all developers of free software, in this case, OpenStreetMaps. And then lastly, we have a blame indicator. Who was responsible for this and what are the notes that they may have taken? In this case, this rule was built by our CEO, Sridhar Ramaswamy. Note here that I don't include any type information. We don't need to, because the type is encoded in the object of the predicate. So in this case, founded, the schema for founded, P571, the object is necessarily a date. So I don't need to do any type of type declaration in my system. I can rely entirely on the type declarations that are already in Wikidata. Now I just need to write transformers that for each type that I care about, common units, strings, dates, etc., into a form that we can more easily represent in our data, and then do last minute rendering. So going back, here is an example of the human rule. So the name of the rule is human. Its predicate is that it is an instance of the object human, and then it has these rules. Now, one place where this really came in handy, this like exploration and iteration, was we naturally, I think, or naively, assumed that companies have one CEO. But as we were exploring the data, some of the examples were showing us cases where companies like Netflix have more than one CEO. Because of that, we needed to change the singleton to a list. So we could add a much, much more complicated predicate language to extract these, or transformers. Maybe we only want the current CEOs, not former CEOs. But we went for expediency here. So we went for the simplest possible definition. The output of this tool is a intermediate representation, a program, if you will, as you see here, represented in a YAML file. And then this program gets executed by PySpark. So PySpark is a MapReduce framework where you can write Python programs. And what we do is we take as input one of those JSON entity representations. And then we have an interpreter that interprets the program that we just specified earlier. And then it outputs a representation like you see on the right-hand side. Now, that's all well and good when things are one hop away. And for most of our cases, things were, in fact, one hop away. They were just predicates on a given entity. We decided, and by we, I mean an intrepid product manager of ours, decided that we should show senators for states as well. Wikidata does not have an edge from a state to its senators. In this case, we want to show Dianne Feinstein as the senator for California, but there is no edge from California to Dianne Feinstein. Because of this, we're not able to just extract that as a fact when we process the data as I described before. However, there is an edge from Dianne Feinstein labeled position held with object United States Senator with attribute electoral district of California Class 1 Senate seat. California Class 1 Senate seat has an edge labeled located in the administrative territorial entity that points to the object California. So there is hope. We can do this. So here's how we do it. We actually load all of Wikidata's flat JSON data into our key value store. We key it by Wikidata entity ID. Now we have a poor man's knowledge graph. And instead of writing complex Sparkle queries, we can do any type of computation we want, so long as we can inspect or query by a subject or an entity itself. So in this case, we take our Wikidata dump, we pre-process it. So we have another Sparkle job, or sorry, another PySpark job that goes over Wikidata. It finds every entity in Wikidata that has this is instance, this is just an optimization. And then it attempts to see if there is a path that can be satisfied with this edge path. So specifically, we're trying to find humans who have a predicate position held. And if they don't, if anywhere in here, these constraints do not match, we abandon. So we're trying to find position held US Senator. And if that's true, then we look at the qualifiers on that US Senator and we check their electoral district. Now, notice there's no entity here. There's no object here. There's an implied object. So if this were Sparkle, this would be an unbound value. This unbound value was then used to look up in Scylla. So we'll find, in this case, it's the, what was it, California 1st District or 1st Senate District. We will look that up in our Scylla key value store because we have that entity as the object of this predicate here. And then once we have that, we'll chase that next edge. Given that entity, we'll then look at it's in the administrative territorial entity, which is P131. The object of this is California in our Dianne Feinstein example. So now what we do is we build a really simple database that says when the entity is California, there is an inversion rule that knows how to generate the field senator, and it has value Dianne Feinstein, which was the original input to here. Okay, so we've just inverted the data set. Now, luckily, this is not very common. And as such, we can load all of this into memory when we do our next phase. So as we described earlier, when we, we can just load that into memory. And as we are encountering one of these transform rules, we can say, okay, California is a state. There's an inversion rule. And then when the inversion rule is set, we'll look up in that database that's in memory to see if there's a corresponding value that we have pre-processed. If there is, then we render it exactly as we did before. So again, we're pushing as much work to build time as we can. Yes, it's a little slow to process this data set twice. It's about a terabyte. It takes, depending on how aggressive you are with machines, anywhere between 30 minutes and an hour. So now we have to do that twice, but who cares? Compute time is free compared to engineering effort and user awareness effort. So now we have our P0s out of the way. These are the things we absolutely have to have in order to launch a product whatsoever. So the next task is to build pretty pictures. So the first thought we had was, well, Wikidata has this nice predicate called image. So we can just extract that and move on with our lives. But for some reason, I decided to take a look at some entities, and I discovered that in the case of the entity Forrest Gump, its image is this wonderful wax figure you see here on the left. And if we showed that to our customers, I'm pretty sure they would be pretty dissatisfied. However, the image on the corresponding Wikipedia article is great. It is the original art from the poster for the movie. So given this, we decided to not rely on the image from Wikidata, but rather to rely on the image from Wikipedia. So Wikipedia publishes its own data in two formats: the Wikimedia markup, and also as an HTML preprocessed dump with all media assets in it called a Zim archive. So we're able to take that HTML and just simply process it and look for this image here, an image inside of an info box. And once we have that, we're able to just pull that image out and then find the corresponding image asset in the archive. And then that's what we render. We further transform this because these images tend to be quite large. And again, our users demand speed. So we rescale it, we resample it to make it load incredibly fast for you. Lastly, we need concise summaries. So going back, if you look at the Bing and Google and Neva examples, you'll see the summaries are all about the same. And the answer is we all get them from the same place. And that is the first paragraph of Wikipedia. Wikipedia's editorial style guide says that the first paragraph of each article should be a concise summary with like the first sentence being the thesis of who this person or thing or whatever is. So all we need to do is find the first paragraph in the Wikipedia article and then transform it into something that's usable. And that's all we do. We find the first paragraph, we strip out all of this pronunciation guide, we strip out the superscript for footnotes, and then that's what we render. Now, another thing that our users, we launched with our P0s and we launched with these two P1s, and then our users started giving us good feedback. And the first piece of feedback that they wanted was for us to have maps for cities and states in the entity, because this is what the other search engines do. Wikidata does not have a map exactly. Wikidata will tell us the bounding box of a map. So they'll say, here's the northwest coordinate, and here's the southeast coordinate of a bounding box that contains this region. But that's not sufficient for our users. So what we did instead is we found another data source. In this case, there is a data set called OpenStreetMaps, which is an open source. We can call it the Wikipedia of analog to Google Maps. And in its database, not only does it include things like cities and maps and stuff like that, but it also includes the shape. So this is the exact boundary of Palo Alto. And here's the center of Palo Alto. And it includes pointers to the Wikidata entity itself. This was immensely helpful. I didn't have to do anything clever about matching. It gives me a primary key to look it up by right here. So going back, we make our build pipeline even more complex. We push, when we process an entity in our build pipeline that looks like it might need a boundary, so it's a city or a state or a country, then we look up in our copy of OpenStreetMaps this primary key, so whatever the entity is that is associated with it. We fetch this, we filter it, because maybe this boundary is too complex to render, because these shapes can get pretty complicated. So you need to shorten the number of points in the boundary so that you can render it quickly. And then that's what we actually store in our intermediate representation. So now we have our P0s done and we have our P1 done, P1's done. So next it's time for our P2s. And like all good projects, P2s are the things that you just don't get to, and they're the things that you'll do when the interns get here next summer. They start in about 2 weeks, so I'm very excited. So the first thing that we're going to do is we're going to build a system that listens to a data feed from Wikidata that will tell us every edit to Wikidata. And whenever that happens, we will then asynchronously issue a re-indexing of all of the things I've described before. Because we already have Wikidata stored in Scylla, we don't have to batch process everything. We can do it in an ad hoc way. So in the unfortunate event that a notable person passes away, we can see that update on that attribute. We can fetch that entity, apply the diff to it, and then re-render the entire knowledge panel. The number one case where this is important is when notable things happen, so elections. So the President of the United States, when an inauguration happens, you don't want it to have stale data because it makes you look silly. And then in the other cases, when someone passes away. These are the two main cases where our users give us feedback about staleness being an issue. And secondly, another thing that would be really great is to have categorical pivots. So you might imagine someone searches for Steven Spielberg movies or list of notable people from Alabama. Then on other search engines, that gets rendered at the top as a list of entities. This we have not built yet. This is a thing that will likely, we can either pre-process the vocabulary of these, just decide on which ones we're going to support, pre-process, store them, or we can actually have, as you were just hearing about a moment ago, we can have some transform that takes whatever the user's request is, converts it to a Sparkle query, and then renders it in real time. We haven't decided which one of these we're going to do yet because the interns aren't here. So here's the fruit of all of our labor. Here's the query Albert Einstein on Neva. And on the right-hand side, you can see our knowledge panel. We're going to add more images so we can be like the other fancy search engines, but I think this is a pretty good start. We have user locale dependent date rendering. We have user locale dependent unit rendering, and we have the notable attributes that we care about. So to summarize, the trick that we decided to do was, in order to hit our latency requirements, we shifted as much work from serve time to build time as we possibly could. To do that, we used a really heavy PySpark job to process Wikidata JSON dumps more than once in order to get all of the transforms we needed. We built a Scrappy tool for allowing multiple engineers to work at the same time to define the programs for extracting and building our presentation layer. And we serve things out of Scylla. As I described before, it's a key value lookup. We key it by Wikipedia URL. Right now, we're not doing anything fancy. We're just looking at the presence of a Wikipedia result in the top of our search results. We trust our search results. And so if we see Wikipedia, then we are pretty confident that we should show this. And then we use the user locale information and anything else to do last minute transforms of the intermediate representation for the user. And then finally, we used gaps in Wikidata itself, like for example, the summaries in the image or with the political boundaries. We used other data sets to supplement that as possible. And now all of these are part of our internal knowledge graph at Neva. We use this knowledge graph not just for knowledge panels, the thing on the right-hand side, but we also use it for some natural language understanding of queries, so that when users say, I want the weather in Charleston, South Carolina, or Charleston, we understand that Charleston is likely interpreted to be Charleston, South Carolina, based on where the user is, amongst other things. And so, yeah, that's it for me. Please reach out if you have any questions. I'm Nathan@neva.co. That is not a typo, .co. And if you're curious about Neva, you can read more about us at neva.com. And as always, we're hiring. Thanks.
Thanks, Nathan, for that great overview of the knowledge panel that you all are building. I see there are some questions from audience.
Yes, I think the first one is for you, Vinay.
Yeah, so the question is, are the same set of interaction paradigms also suitable for write access to a knowledge graph, or do we need different kind of interaction methods for that? The interaction methods I presented, they were actually gleaned from read access. They were not meant for write access. I have not done analysis of how users are updating the knowledge graphs. So that would be a separate discussion.
So I can give you some comments there. At eBay, I was a part of an externally facing search engine. And in JP Morgan, we have applications that run internally. So I think the set of users are very different. In the eBay case, it is very adversarial. So we have to use a lot of other techniques, more robust techniques to allow users to change information on our eBay knowledge graph, like community, all the things that you see on Google, etc. What I'm finding here in JP Morgan is the users are extremely trusted, vetted, everyone is logged in. They're high value business users, and you can actually use all these techniques for them to allow them to actually update values on our knowledge graph. So that's a big sort of contrast I've seen in these two different applications.
Yeah, I mean, I guess in the case of eBay, they are all unpaid, right? They are free people on the internet. And in JP Morgan, they are probably highly paid professionals, right?
Yes,
So,
and completely authenticated. If you see someone doing something, we exactly know who that person is. We have a whole HR system to take action, all those. So very safe usage of no adversarial kind of use cases.
okay.
But would love to know anything that Niva uses from the community to help correct the knowledge graph or something.
So we're just now, we are actually building a community tool into Neva. So Neva is different from the other search engines in that our users are always signed in because it's a subscription service. They have a relationship with us and they're always signed in. Because of this, and we have identity, some of our users are now trusted users who are part of our community program. And we're building out the ability for them to affect the search results or propose edits. So we're not necessarily just giving carte blanche and saying, hey, go edit our knowledge graph or go edit our search results, but they're able to propose modifications. So the first way you do this is by like giving people the ability to exclude things like, hey, I issued this query, this is the wrong interpretation, suppress this video or suppress this entity. Now we're actually building the opposite or something much more in depth, which is, can we actually take proposals for modifications to what we're showing in the form of the knowledge panel? And further, once we accept that, in addition to applying it on our side, can we propose that gets pushed back up to Wikidata itself? So that's the type of system that we're looking at this summer.
Thanks. So Nathan, we have a question for you here. For the lower latency requirements, you mentioned that much of the data is static. Mm-hmm. How do you handle real-time data such as breaking news, etc., those modules?
Sadly, today, right now we don't. So in the case of notable people passing away, like this leads to embarrassing things on our side. To fix that, we're going to do exactly as I said for our intern project. We're going to be, Wikidata publishes edits to the graph. Particular edits we're going to use as like a prioritized re-indexing or reprocessing and re-indexing. Things like people passing away or things that are date related seem like obvious things to prioritize. Another thing I forgot to mention, and this is mentioned in our blog post about this knowledge graph, is that we have, after doing this, we've discovered that Wikidata themselves are now building not just a knowledge graph, but a presentation layer and a streaming service. So it is possible that as they flesh that out and it becomes a mature product, I will happily throw all of this code away and instead pay them for a great service that is always up to date. So the answer is we don't do anything today, but we'll be doing something when the interns get here in a couple weeks.
Thanks. Vinay, there's a question for you. Is there a user experience example that starts with a high-level abstract visualization and helps the user to drill down as described in your great presentation and design principles?
Yeah, so I think the map search or apartment search example is an instance of that, where you're first presented all these choices on a map and then you can drill down. In Google Maps does that too, right? You type in an address, you get a search, and then you can zoom in, and then you can get the street view, right? Google Earth interface is a great example of that.
Also, I think Redfin and Zillow use very similar things, but at a higher level, they will just show you counts of the houses mm-hmm. in the various regions. And then as you drill down, they will show like the prices and other things, but at a higher level, they try to show statistics on the various areas. And another question for Nathan, could you comment about the infrastructure you use to run your knowledge graph?
So we have explored running our own copy of graph databases, but what we've discovered is that for most of our use cases, it's more beneficial to do as much pre-processing as we can and just key things in a key value store. Because once you have something keyed in a key value store, if you have sufficient data in the value, you can chase edges and you can do a poor man's ad hoc version of a graph database. So we tend to use the Wikidata Sparkle interface for data exploration to figure out what types of transforms we may want to use in order to then optimize for whatever our use case may be. So in the knowledge panel use case, we flatten everything using everything I just described. For the case of doing named entity recognition for places and such, we have a similar pipeline, but it's customized just for that task. Instead of worrying about presentation layer, it's worried about things, attributes such as population size or popularity that you can get from Wikipedia. These are attributes that we can use to bias the conditional likelihood of a user in a particular location means a particular named entity. We had to do all these tricks because we still don't have a huge user base. A company like Google or Bing, they have millions of users that are constantly giving them feedback, and so we're having to find external data sets in order to kind of induce these. But in all cases, so far, we found that it's just as good for our use cases, which are usually latency constrained, to pre-process everything and store it in either DynamoDB, which we experimented with first, or later with Scylla as a key value store.
So Nathan, one question I have for you is, do you understand your user? I mean, why are they coming, what are they looking for when they're typing search queries?
I mean, that's the fundamental task of all search engines, is to understand what the user is intending when they issue the query. And in order to do that, you can use various pieces of context. We understand where the user is based on IP and things like that, or device location if the user has granted it. We understand some historical information about the user's interactions with the search engine before. So if they've searched for lots of athlete-related things, then it's likely that the next query is related to athletics. So our goal is that since the search engine is a signed-in experience, then we can in fact leverage some pretty powerful personalization on behalf of the user. And so in order to do that, we're starting to build systems that can do some form of agglomeration over attributes that the user is accumulating. We're in the very early phases of this. It's a trade-off between how do you do this in a sensitive way for the user and how do you do this in an effective way to give them the best results. So right now, we started with doing things completely automatically. Can we just build automatic rankers that are all like collaborative filtering? And then we've swung the pendulum completely the other way, and now we have declarative statements. Users can express their interests or the sources they trust. And now we're swinging the pendulum back toward the middle, where there's a combination of users expressing their relationships and the things that they're interested in, and then having machine learning rankers on top of that.
Thank you. There's a question here. What's something Niva initially considered doing in the area of knowledge graphs, but was ruled too ambitious? Have you decided which applications were in scope, etc.? And I have a related question to this, which is on the web, etc. I've seen applications of knowledge graph are only traversals. Like you see this pane, and then you can keep clicking and hopping. Are there any more that can be implemented as like in any database or something? Have you seen more complex applications of knowledge graphs on the net that uses, for example, helps you find the shortest path or something like that, like LinkedIn or?
100 years ago on Facebook, Facebook used to show you the shortest path between you and any person you were looking at. This is when Facebook was primarily for students, and so you could find someone in your class and find like the neighborhood of you and that person to see the relationship. But actually, I haven't come across too many applications of what you're talking about, mostly because shortest path is, it's an n-squared algorithm and something that big to do all pairs. And so it's just too big for most use cases. It'd be interesting. I haven't come across it. Now, the other question was, what did we decide not to do? So when I first set out on this, I was like, well, while I'm building these knowledge panels, like, let's just shoot for the moon and let's also build a question answering system. And let's go ahead and build these these carousels at the top of all of these pivots. And it was about 3 hours into the process that I was like, man, this is just too much work. Because I was hoping initially that loading things into a graph database that we serve locally, and then just turning everything into a bunch of Sparkle queries and then using structured query processing or even natural language processing, that we would be able to do these things. But it turned out that it was just going to be too much engineering effort given the time we had. So hopefully all of that will happen sometime in 2021. Let's be ambitious.
Thank you. So Vinay, we are all done with the questions.
Yeah, so I have
here in the panel.
Yeah, I have a question for Nathan. I was intrigued by your Diane Feinstein example. And, part of me was saying that, wow, this is really cool because this is illustrating that in the knowledge graph, as long as, there are links you can traverse, you can conclude the right things because you know what the links mean, right? But on the other hand, my NLP friends would say that, or even some of my data science database people might say that, well, why are you using Wikidata? I'm sure you can find a different data set where that connection is explicitly present. Or the NLP people would say that, well, we can figure this out by text extraction, right? So, I mean, you're using a lousy knowledge graph technology, right? So how would you respond to that?
So, in fact, in a former life, I worked on a similar project at Google where we were doing natural language. We were building knowledge graph construction by processing natural language text. Specifically, I was working on building, extracting hypernyms from text. So like Dianne Feinstein is a senator, not necessarily is a senator of California. And the thing I learned is that natural language processing and natural language understanding is a shockingly hard problem that is prone to many errors. The main error being that not only are there technical problems, but it's now you have a problem of understanding the validity of the data. The great thing about Wikipedia is that there's an active community of editors who are enforcing a set of guidelines on the quality of the data. As you just read unstructured text on the web, just blogs and such, you can end up with some pretty bizarre assertions. One particular example was when I worked on this project at Google, was that sadly, the number one thing that we extracted for Barack Obama by frequency was terrorist. Now, this is just what happens when you process the web in 2012 or 11 or whatever it was. It's the zeitgeist of that particular part of the web we were processing. And so it's much harder to build some type of ontological reasoning type thing on top of it. You can go in and you can do really complex things like Google did with the Knowledge Vault, which tries to reify this data into the existing knowledge graph, into the existing schema. But this is a really, really difficult problem that involves like tens to hundreds of engineers. And given our constraints, we decided, you know what, off the shelf, good enough. And so that's exactly what we did.
So what about the criticism that couldn't you find a better data set which directly curates that Dianne Feinstein is a California senator?
Always happy to take more data sets. Like it's also, I don't know what I don't know. And I started with what I knew, and that was Wikidata and Wikipedia and DBpedia. It's quite possible that there are other data sets. And as we've seen with OpenStreetMaps and we have some other data sets we're importing, we're being very tactical about data sets that we import. And as long as we can find a join key. So for example, we also have like movie showtimes, or we have where you can watch or stream particular TV shows. As long as we can find a join key between our internal knowledge graph and these other data sets, then we can look these things up. And so we're building point solutions for all of these things as they come up. The goal, the dream is to have a general solution to everything, but It's often easier to just trade 10-point solutions for the engineering effort involved.
Okay. So we are nearly at the end of the class time. Any final words?
I just want to say thanks again for everyone for having me.
Sure, yeah. And I can announce our session for next week. Next week, we will be, not next week, this Thursday, we have two speakers. Bob Kowalski, he will be telling us about a structured query interface based on logical English. And we'll have Michiharu Yasunaga, who will tell us about posing natural language questions against knowledge graphs. So this should be a very interesting discussion, and they would present a sharp contrast between the two approaches. So we look forward to seeing you on Thursday. Thank you, and bye for now.
Thank you.